Hi friends, welcome back. In the previous chapter, we derived setup and hold equations of a flip-flop. So there, we didn't include the effect of any kind of clock uncertainty for the setup and hold timing equations. So in this chapter, we are going to incorporate the clock skew in our setup and hold timing equations, and we will see how the clock skew impacts the setup and hold equations. So let's get started. So here first we are going to take the positive clock skew. So first let's understand what is positive clock skew. So as you already know, this is our capture flop, this is our launch flop, and this is our capture flop. So the data is always launched by the launch flop and it is captured later, ideally one clock cycle after the one clock cycle by the capture flip flop. Okay, so if you see in the waveforms, this is the clock 1 which is corresponding to the register 1 flop, or this is nothing but our launch flop. This is the launch edge and this is the clock 2 of our capture flip flop, and the clock edge at which the data is captured is nothing but this, and this is our capture edge. So here if you see, there is a delay between clock 1 and clock 2, which is nothing but T skew, and this is coming because of the delay present between clock 1 and clock 2 point. Okay, so ideally the data is launched at this clock edge, and now it will get captured by the next clock edge of clock 2, which is here. Okay, so if you see this, ideally when there is no clock skew, we saw that data is launched at this clock edge and it is captured. So there is no clock skew, so this edge will be basically coming here and this will be coming here. So the data is captured at this clock edge. But once there is a clock skew, the capture clock has shifted by the T skew time, and now the capture edge is coming here. So actually speaking, the delay between the capture data and the launch data, or the delay between the launch and the capture point, has increased by T skew time. Now let's see how this T skew will come in our calculation of setup and hold equations, and how it will impact the setup and hold timing constraints. So now with positive clock skew, so ideally speaking here, positive clock, this is positive clock skew because the delay is getting increased between launch and capture flip flop. Okay, so that is why this is positive clock skew, and you have to remember that in positive clock skew case, so this is the data flow, right? And the clock is also going from register 1 or from launch flop to the capture flop. So the delay is getting introduced in this path. So both the data flow and the clock directions are in the same way. So the clock skew introduced in this case is nothing but a positive clock skew. Now let's see with positive clock skew how setup equation and hold equations will be impacted. So as you saw in our previous chapter, where we derived the setup and hold equations without incorporating the clock skew, our setup equations was this one. Here just the red T skew. If we just remove the red T skew, then whatever remaining is our setup equation. So the idea of setup equation is the total propagation delay when the data is launched and when it reaches to the data input pin of the capture flip flop. So this delay should be less than the clock path delay. So the data is launched at this clock edge and it reaches at the capture flip flop at this clock edge. So this total propagation delay, total data propagation delay should be less than this clock period minus the T setup. So basically the data should reach before this point. Correct. Now here in the positive clock skew case, basically the clock has shifted by t skew time. So now our new point where the data should get captured will be this clock age minus the t setup time. So here basically we have to include the clock skew in the required time. So our required time actually has increased by t skew time. Okay, so now the new setup equations will become clock to Q delay plus combinational delay should be less than clock period plus t skew minus ka t setup. So if you see here our clock period, if you rearrange these equations, our clock period will become greater than or equal to this value. So basically if you see here the clock period, the required clock period to meet the setup requirement has decreased by t skew time. So if the clock period decreases, the frequency of operation of the design will increase. So basically with positive clock skew, our design can work at a higher frequency. So here the required time has increased by t skew time, and the arrival time is going to be the same. Now the setup slack will be required time minus the arrival time. So here the required time has increased. That means our slack is going to be increased in a positive direction. So slack, when it increases in the positive direction, it is always better. So as I said, since the required clock period with positive clock skew has decreased here by t skew time, that means our design can work at a higher clock frequency. And what we can conclude from here is positive skew improves the performance. It basically improves our setup slack. So hope this is clear. Now we will see the impact of positive clock skew on hold equation. So in ideal case, if you see, so here you can see the waveforms with t skew incorporated, but in ideal case if you see, this is the clock 2. If you see the clock 2 in ideal situations, it will be the rising edge will be here and then the rising edge will be here. Okay, so if the rising edge is here, then we have some hold time here, hold requirement, hold time of the flip-flop, and that will be our hold requirement. So the propagation delay of the data should be more than the t hold time of the flip-flop. But now if you see, our clock edge has already shifted in the right direction by t skew time. Okay, so this is already shifted in the right directions. Then we will have this flip-flop hold time. So this total time will be t skew plus t hold. Now our new requirement will be the data propagation delay should be more than t skew plus t hold of the capture flip-flop. Correct? So now new hold equation will be clock to Q delay plus combinational delay should be greater than hold chart, which we do by default at 0. So this we can consider if at respect to 0. The 0th instance, this value is 0. So let's assume this value is 0. Then the t hold plus t skew. So now our new propagation delay, or how our new equation will look like, the propagation delay now it should be more than t hold plus t skew. Okay, so here if you see the required time will be now this much time, this total time here, which is clock skew plus t hold time of our capture flip-flop. So here if you see the required time has increased by t skew. Now the arrival time is nothing but clock to Q delay plus combinational delay of combinational logic. Now the hold slack is always arrival time minus the required time. So if you see here, our required time has increased. So if our required time has increased, our hold slack will basically decrease. So if our hold slack will basically decrease, then there is good chances that this hold can go in the minus direction. So if this hold will go in the minus direction, that means there is a hold violation. The hold slack should always be positive. And that means what we can conclude from here is the positive clock skew in hold equation always makes it harder to meet the hold requirement, because our aim is to always make the hold slack as much positive as possible. So with positive clock skew introduced, our required time actually has increased. We need more time for the data to arrive from the launch flip-flop to the data pin of the capture flip-flop. So what we can conclude here is always positive clock skew improves the performance. It makes setup timing constraints more easy to meet, but it always makes it harder to meet the hold requirement. So hope the positive clock skew impact on the setup and hold timing equation is clear. Now let's see the negative clock skew impact. So first of all, we have to understand how we are calling it as a negative clock skew. So this is our, again, our launch flow, and this is our capture flow. And if you see here, the clock is first coming to capture flip-flop, and then there will be some T skew or clock skew, some delay will be introduced, and then the clock will reach to the launch flip-flop. So if you see here, the capture flip-flop will get the first clock, and then after some T skew time, the launch flip-flop will get the clock. But the data is always launched by the launch flip-flop and it is captured by the capture flip-flop. So if you see here, the data direction is from left to right, but the clock direction is from right to left. So in these situations, the clock skew, which is introduced by the delay elements between the clock of capture flip-flop and launch flip-flop, is nothing but called negative clock skew. If you see through the waveforms, this is clock 1 and this is clock 2. So clock 2 first the clock 2 will, the rising edge is happening, and after the T skew time, the clock 1 rising edge is happening. So basically data is always launched at this flip-flop, and now when it will get captured, this data will get captured at this clock edge. So this is launch and this is capture. And now when the hold check will be happening, the hold check will happen at this clock edge. So here this is the data and here this is the setup check. Right? So now if you see here, the T skew is basically, now this delay is basically coming from capture flip-flop towards the launch flip-flop, this direction. So this is called nothing but our negative clock skew. So in other words, if you say here, if you see data is launched at this clock edge and it is captured at this clock edge. So what happens is the time between the data launch and data capture has actually decreased by T skew time. So if the data time between launch and capture flip-flop has decreased, this is basically required time. So here if you see, the required time has decreased. We will see in the next slide how the negative clock skew will impact the setup and hold timing equation. But in this slide, let's concentrate on what is negative clock skew. So hope this is clear. So the negative clock skew is basically when the data and clock directions are in opposite direction. And how the setup and hold check will happen in this case? The setup check will happen at this point and the hold check will happen at this time. So the hold check is happening actually before the T skew clock time. Okay, so this is the hold check. Ideally the hold check happen at the same clock edge. So if there is no clock skew, the clock 2 rising edge would have happened here, but it is happening now before the T skew. So the hold check will happen before T skew time. Okay, now let's see the impact on setup equation. So here the T skew is always less than 0. It is negative. Now let's see the effect of this on the setup equation. So ideally speaking, if there is no clock skew, just remove this T skew, this term, and we have the clock to Q delay plus combinational delay should be less than clock period minus T setup of register 2. But now the T skew, negative T skew has come here. So now this time, this term, what this term will become? So what this equation is saying, this delay should be less than this clock path delay. So this is the clock path delay. So the data is launched at this clock edge, and now ideally at this clock edge minus setup time. That was the term corresponding to this. Correct? Now, because of the negative skew, actually the capture rising edge has shifted towards left by t skew time. Correct? Now we have to meet this requirement in t skew time less. So here we have put minus t skew. So this minus ka t skew has taken care of the t skew is less than 0. So what we don't have to put the extra minus here. We already have taken care of minus negative clock skew by subtracting the t skew time. So just visualize it and just understand that now the required time, actually the required time in ideal case, the required time was clock period minus ka t setup, but now the clock edge itself has shifted left by t skew time. So now the required time has basically decreased. So now the clock period, if we rearrange this equation, clock period has increased by t skew time. So if clock period increases, our frequency decreases, and if our frequency decreases, that means our design can now only work at lower frequency, right? So if you see the required time, so now the required time has decreased by the t skew, and arrival time is again going to be the same. Now the setup slack will become required time minus arrival time. So required time has decreased, required time has basically decreased, right? So if the required time has decreased here, that means our setup slack will also decrease. So negative clock skew basically degrades the performance of our design. Always remember that with negative clock skew, our required clock period to meet the setup requirement has to be increased by the t skew time, and hence the frequency of operations will decrease. So always remember, positive clock skew improves the performance of our design. That means our design can work at higher frequency, but negative clock skew degrades the performance. Now let's see the negative clock skew impact on hold equation. So now this is our, as I discussed earlier, this is our hold check. Hold check is right. Now without the negative clock skew introduced, if we remove this t skew, this term, then this is our equation. The propagation delay should be more than hold check at 0. Let's consider this as 0 and t hold. So basically, if this would have been our this would have been our there, if in the case of no clock skew, negative clock skew, this would have been our hold check rising edge, and just consider that this is the t hold. So the propagation delay should have greater than this time. So in ideal case, if this was the hold time, and now if the rising edge had shifted this time left side by t skew, so now basically this will decrease our required time. So required time was t hold check 0 at 0 plus t hold, but with negative clock skew, the hold check has shifted left by t skew time, right? So now our required time will become t hold minus t skew. So required time has basically decreased here. So if you see now the hold slack, so the hold slack is arrival time minus required time. Required time has decreased. So now hold slack will increase. It will increase in positive direction. So with negative clock skew, actually our hold slack has improved. That means negative clock skew, actually it's easy to meet the hold requirement. So always remember, negative clock skew degrades the performance. That means it reduces the setup slack, but it increases the hold slack, or it makes it easy to meet the hold requirement. So I hope the impact of negative clock skew on hold and setup timing equations is clear. If you have any doubts, please write down in the comment section. Also, if you liked this video, please hit the like button and do not forget to subscribe this channel so that you will get all the notifications of my next videos. Thank you very much.